I'm going to invite the second speaker, the first English-speaking speaker. But before, I want to say that if you are Ukrainian and you would like have Ukrainian subtitles, you can. There is button on the bottom, show captions. You can have titles in Ukrainian. And also, if you are English-speaking participant, you can have captions in English. There are few Ukrainian speakers. If you don't understand Ukrainian, you can use captions. It's my great pleasure to introduce to you a remarkable speaker who has made significant stride into Rust programming community. Please join me in welcoming Maciej Hirsz. Maciej began his journey with Rust back in 2016 and quickly transitioning to working with it professional in 2017 at Parity Technology. Since the time, he has amassed a wealth of experience, knowledge, contributing greatly to the field. Nowadays, Maciej divides his time between his own open source projects, painting, tabletop games, and managing the lively activity of his 5 cats. Today, Maciej will present a talk titled Tokens All the Way Down. In his talk, he will guide us through the basics of lexing and then demonstrate series of the optimization technique to a simple lexer example. Who don't know, lexing is part of this long parsing and compiling tool chain. It's the first stage. Whether you are keen interest is in the domain, it will be useful to you because it is not only about lexing, but also about optimization. Okay, without further ado, please join me in giving a warm welcome to Maciej. Maciej, please.
Hey, yeah, let me share the slides. And there we go. That should work. Okay, cool. So hi, I'm Maciej, as already said. So welcome to the talk. The talk is tokens all the way down, or how to pass strings to tokens at roughly 1 gigabyte per second, or gigabyte per second. As already said, yeah, I started my learning Rust in like 2016, so it's like at the very closely after the release of 1.0. So early times before like a lot of nice things landed, like lexical lifetimes and stuff like as annoying as borrow checker is now, it was way more annoying in the past. And then professionally started working in Rust at Parity at beginning of 2017. I'm the author of Logos, Cobalt, and Amherst. These are like main open source projects that they all need some love now, but we'll get there. You can also ask me anything about proc macros, because it turns out like pretty much everything I do, I just use proc macros because I like it, and because it's, I don't know, it's difficult to like tickles my brain. You don't have to worry though. This talk is not about proc macros, but like it's just tangential. I have a website, I have an email, I have a GitHub. I'm not on social media necessarily because I'm old and not cool, and I don't have time to argue with strangers. So this talk is Logos adjacent, and I'll briefly explain it. So back when I was like still like running Rust, I wanted to make a JavaScript transpiler because that sounds like a simple, easy project for one person to do. And I was still working with a lot of JavaScript, and I was like annoyed by compile times of JavaScript to like bubble and stuff. So I was like, okay, well, to make a transpiler, I need to write a parser. To make a parser, I need to write a lexer. So I wrote a lexer, and once you write something in Rust, you can play this fun game where you start benchmarking your code and seeing like performance improve over time. And I got the lexer eventually to like the performance I wanted to have, but I ended up with like a very verbose code that was kind of hard to maintain. I didn't necessarily have to maintain it because like JavaScript changes every 3 months or something. But I figured, okay, I can learn proc macros, and I can try to separate the structure of how the lexer is built into like its own like code generation, and only have like the definitions of the tokens defined in the code of my lexer. So that's how Logos was born. So Logos is basically what Logos is Logos is not a lexer. Logos is a lexer generator. So it's basically a glorified proc macro that takes like a definition like this on the screen now, where you write your token definitions as a simple enum, and you give you define the tokens as either like simple strings, or you can use the regular expression syntax to define, okay, the text is like, lowercase letter, uppercase letters, and plus, which means like one or more. Important note on Logos: the Logos doesn't use the regular expression engine. It only uses regular expression syntax. So there are some limitations on like backtracking and stuff if you ever like decide to use Logos. But that's not necessarily what this talk is about. So I'm going to talk about some optimizations I've learned while I was working in Logos and as some other projects. And lexing is a pretty niche domain. Like not everyone needs to write lexer. But the optimizations themselves I think are pretty broadly applied. And like whenever you like deal with like parsing text, or even like parsing like binary code, or if you want like do some bytecode or something, like all of the stuff in the stack is like applicable. So if I do my job right, you have learned something here, no matter what level you are, hopefully. Very briefly, what is lexing? So if you have like some inputs, like so we're gonna assume this is kind of example of like, okay, I want to like parse some source code of a programming language of some kind. So this is like a simple hello function from JavaScript. I want to do something with this JavaScript code, right? And the first thing you probably want to do is to change the input from a stream of bytes or characters for the text into a stream of tokens, which would look something like this. So you want to divide the source code into individual tokens, and you want to differentiate between tokens, right? So you want to know that, okay, function and hello, like they're both like, for us like humans, they're words, right? But for the purpose of like the language, they're actually different things. Like the function is a function keyword, it's a different like entity, versus hello is just like identifier, which is like a any word that's not a keyword. And then like all the like parentheses and brackets and punctuation and stuff, like you want those to be separate tokens. That's roughly what lexer does, right? What matters, so lexer is basically like a first step pre-parser that you want to build into your like full parser. Let's split the source code into tokens, or we also call them lexings sometimes. And why you do this is because it makes it much easier to then create a parser that parses the entire source code into abstract syntax tree. I'm not going to talk about some abstract syntax tree, but this is like if you want to look further into parsers and all this stuff, like if you just search abstract syntax tree, then it's going to give you a lot of information on how to do stuff. All compilers, all IDEs, pretty much all linters, all of them operate on ASTs, and all of them at some point probably use lexers, because you don't necessarily need a lexer if you want to write a parser. And like if you have a simple enough problem, like like if you want to like parse something like JSON, you probably can go straight from JSON to JSON text to a tree without the lexer step. But for anything complex enough, like a programming language, you probably want to like have a lexer, because even though lexer is a tiny bit of a performance cost, dividing your parsing to a lexing step and a parsing step to a tree makes the whole process much simpler to understand, makes your code much more readable, much more easy to maintain. So pretty much every programming language that uses any like compiler-oriented ID, they all use a lexer, right? And like if you ever like seen like an error, like syntax error or unexpected token, like in JavaScript engine, whatever, it's a parser telling you like, it has encountered a token from lexer that didn't expect that this time. And lexing is also like often quite often the most like work intensive step for like parsing to AST, simply because like your source code has way more bytes than those have tokens usually. Like every identifier has more bytes than it has. It's one token, but it's like multiple bytes. And you also have like white space and stuff, and sometimes maybe comments you don't have to parse. So just by the amount of iteration you have to do in the lexer can be like the bottleneck. So writing a fast, if your lexer is fast, your parser might be fast, but if your lexer is slow, your parser will be slow. So let's write a lexer, right? It's something. We're gonna do something very simple because I want to fit all the codes and slides, and so this is not any particular language. I'm just gonna make something up to have something we can like run benchmarks again and again fit on slides. So my imaginary language, I have only 4 tokens. I have white space, which is just the space character. I don't handle tabs, I don't handle enters or new lines, anything. Just the space character. Then I have a identifier, which is Latin characters A to Z, capital Latin characters A to Z, the underscore character, and the identifier can be any of those characters, 1 or more repeated, right? So foobar is an identifier. The number is same as in the identifier, but even simpler because it just the digit 0 to or all the way to the digit 9, 1 or more. And then I have 4 operators: plus, minus, multiply, and divide. And operator is like the only token here that's always only a single character. It doesn't repeat, so there's going to be some differences in code. Next, I'm going to define my lexer. Lexer itself is like as a structure very simple. So I need some source code that I'm going to read. So this is just reference to the string, and I need to have a start and end of a token. One thing you can see, like I don't have like for identifier or number, I don't actually put the values of those tokens, like or what the actual text in the source code is. The way I like to do things is the token is just like simple enum with no values. And then if I need to read the value of the actual, like, okay, what is the actual string of the identifier, I can use the start and end on the lexer to give me a subslice of the source code at those indices to give me the text when I need it in the parser, right? And for many tokens, you don't necessarily need the source, like a plus is a plus. I don't need to go back to the source and tell me that it's a it's a string size of 1 byte that says plus. I know it's a plus because that's what the token is. So we're gonna start to write our lexer. The way I write those methods, I'm not gonna write like constructor for the lexer. I think that's you can figure it out. Like, okay, you're gonna take I'm gonna take a source and I'm gonna set start and end to 0. That's roughly it, right? You probably would want to write this method as the part of the iterator trait, the next method on the iterator trait. I'm gonna name them, give them name, make them named methods just for the purpose of this talk, because we're gonna go through a few of these at different variations, right? So our first attempt is it's naive lexer that just returns an option of a token, right? So we set our start to an end, right? Because we are beginning a new token. So whatever the end of the last token was is probably gonna be the beginning of the current token. And then we get the chars. It's a mutable value because we're getting a mutable iterator to characters, right? So if every string in Rust you can get a iterator on characters, that's a nice thing built into Rust. And then we do a match expression on the next. So this is okay. Give me the first character if there is one. Give me the first character in the source code or at the start of the token. So slicing. And then you just do pattern matching, right? So if it's a if it's space, then it's gonna be the white space token. If it's lowercase or uppercase or underscore, then it's gonna be the identifier. 0 to 9 is gonna be a number, and then operators are operators. I've hidden the code for the white space and the identifier because those are roughly identical to what the number is. which is roughly this, right? So that's what the branch is. After we match the first byte, we increment the end by 1. And then in a loop, we also check, okay, while the next character is also the same pattern, right? So 0 to 9, same pattern, 0 to 9. And that's identical in the identifier, just with more definitions. So while we still match the same byte, or the same pattern in next byte match, when the next character matches the same pattern, we increment the end by 1 again. And if we don't find anything, or when the loop stops, then we emit the token number. The same is true for the operators, except we don't have the inner loop. We just increment the end by 1 and just emit the token. So that's the entire code. That's like our naive implementation of lexer. It's fine. There's nothing wrong with this. Like, and in fact, if you write like this, just because you write Rust and this is all like systems programming, this is already plenty fast. For most use cases, it might be actually good enough. But we can do better. And the first optimization I would like to talk about, which is like I think very common and very easy win to do, which is to just embrace UTF-8 and avoid the char type altogether. A couple of things you need to know. So strings in Rust are represented in memory as UTF-8 encoded, right? And UTF-8 is basically, as encoding, is backwards compatible with US ASCII, which is a standard from 1960s. It's not changing. It's done. Like it doesn't need to change. There's no reason for it to change. Most of the time, when you're like parsing or lexing source code of a programming language, most of the time you're just interested in the ASCII characters that are there. Like, so again, the standard from 1960s, like you want the letters, the Latin alphabet, you want brackets, parentheses, dots, commas, semicolons. It's all in ASCII. And the important thing about ASCII is ASCII uses byte values from 0 to 127, right? It only uses half of the byte values. And back in the old days, we used to have like different extended tables for ASCII that would use the upper half. Like, so if you use Ukrainian, you would have a different like ASCII table for Ukrainian or Polish or German or whatever, right? And if you then try to like send text between like different computers using different languages, then you would get the garbage because they never agreed like what the ASCII tables are. And like UTF-8 kind of fixes that, where it's like, okay, this is like the one universal ASCII extended ASCII table, basically what it is. But for our purposes, what it's important to remember is that so UTF-8 can encode code points either as 1 byte, which is ASCII, or as multi-byte code points. But the important thing for us to know is that anytime there's a multi-byte code point in UTF-8, all bytes that belong to the multi-byte code point, they all have values larger than 127, which is larger than any ASCII character, right? Which means that if we are trying to find a specific ASCII character as a byte, you never have to worry about a conflict, right? There's like the character for A, lowercase a, that byte is not going to be present in multi-byte sequences of UTF-8. It never happens because you're guaranteed that all multi-byte code points begin with like a bit 1. There's reasons for that. We can look at. It's actually kind of interesting how it's designed. Like UTF-8 is really, really good. It's kind of clever how it's done. And also for our purpose, what's nice about Rust is Rust actually has byte literals. So you can do the same way you write the character literal with a single quote. You can put a B in front of it, and then it's a byte literal. And the same is also true for string literals. You can make a byte slice into literals. Just have the B before the quote. Important difference here is that if you do the B in front of a byte slice, then you get actually a reference to an array instead of a reference to a slice. So like if you needed a reference to a unsized slice, then you just need to do some casting or something. Like you cannot get a fixed size strings because there isn't a type for that in Rust. So let's change our code to just, okay, we're just gonna ignore characters. We know it's actually safe to just ignore the encoding and just look at the ASCII bytes because that's what we're after. So we just changed one thing. We changed the our iterator for the source code from chars to bytes, and then our matching expression, right? We changed all the patterns. from char patterns to byte patterns. So these are just, again, these are just integers from 0 to 127. And all this code is basically the same. Again, we just use bytes next instead of chars next. The patterns change. We just add the b in front of the literals. That's it, right? That's the entire change. We've changed nothing. We just changed to one method. We changed the variable name, and we added a bunch of b's everywhere. So always benchmark things, because you never know if what you did actually has an impact. So our original lexer that used the chars was running at, in my little benchmark that I did, was running at 2.14 nanoseconds per iterator. The new one is running at 1.28 nanoseconds per iterator. So that's 60-70% improvement for basically doing nothing. And that's roughly because we now, our lexer actually does less work, because when I get the next char, the char iterator has internally look, okay, is this the next byte? Is a part of a multi-byte string, multi-byte code point? If so, then it has some work. If not, then even if you never run into a multi-byte code, just always like this extra branch that has to be checked, which we now don't have to do. So it's a win. It's a free win. You can pretty much almost always do this. It's safe. It's fine. And even if you need to then get the string size right, because I'm using the start and end just in the indices, they're going to be the same indices into string, because subslicing a string size uses the byte indexes or indices rather than char indices. So we lost nothing. We just gained performance for doing nothing. The next one, the big one actually, this one is much more involved and much more fun, I think. So this is lookup tables. This is very, very, very old trick that everyone who's been in the field kind of knows about. Lookup table is kind of simple, and what lookup table effectively is just an array. And now, since we are now working with bytes, we can actually make a table. We can make an array of 256 items, which in our case is going to be, the whole table is going to be sized in memory, is going to be 256 bytes sized in memory, which is important. We'll maybe get there. We start with a table. The table is going to be static. It can be acyclic const, doesn't matter. We're going to build it as a const expression. We can do const expression in Rust. So the code here is not going to be super optimal. It doesn't matter that it's not super optimal, because this code is evaluated at compile time, and it doesn't have effect on the runtime performance. So we make a table, just filling it with nonce, and then we use a while loop, because again, this is a const expression, so we kind of limited. We cannot use for loops yet in const expression in Rust. So I'm just going from 0 to 255. I cannot go to 56 because you cannot express 256 in a U8. And then we kind of do the same thing for the same patterns. I just assigned values at the index of a byte. I assign the value of the token for that byte, right? So as a space, the byte, the index corresponding to the byte of the white space is going to be the white space token, and the same for identifier, the same for number, and the same for all of the operators. So that's sort of it. So it's a table filled with nothing but nonce, and then for the indexes that represent bytes of my individual tokens, I put sum of the token value, right? And this is just my static array. And then my next method is now actually much simpler and much shorter. It starts off the same, so I set the start to end. I get the iterator for bytes, and then I use my table. What do? I look up. I take the byte of the source code, and I look up in the table. What should I do with this byte, right? So I cast the byte as a usize to index into the array. Fun part here is, because our array is 256 elements long, even though we don't necessarily need 256, but because it is 256 elements long, and the compiler knows that the bytes next is a U8, that it will never overflow the table. So the Rust compiler will actually, in this example, will automatically omit the overflow checks, right? Because the Rust compiler can prove to itself that this index operation never fails, because it's always, it cannot. the table has enough elements to cover the entire value of U8. So I take my token, I increase the end by 1, and then if the token is not an operator, because all my tokens except for the operator can have multiple bytes, then I go, okay, give me more bytes until for as long as the token at that index is the same as the token I currently have, which means this is the same token. I keep just incrementing in the end, and then if it's not, then I break the loop and then emit the token. Right? This is less code. I think this is kind of simpler also. So how about performance, right? And this is really fast. So we went from originally 214, we went down all the way down to 0.22 nanoseconds. So that's almost a 10x improvement over our naive implementation by using a lookup table, which is really, the main thing. Bonus tip, nesting enums. So I already mentioned that the lookup table is 256 bytes, even though it's an option of a token. So the nice thing about Rust, the ABI in Rust is not stable, so you should not be relying on that, like if you want to do some magic on safe code, but for the purpose of performance of figuring out how large things are on the stack, you can use those heuristics. So an option of a T, enums that like option of a T, will have the same stack as the T that you're wrapping, as long as the T itself has some values in the value space, roughly, that are free. So this is true for references that are not real pointers. So references have the null pointer value that's not, our reference can never be null. So the Rust compiler can use that as the non variant in the option. But it's also true for non-zero integers, the specific types for non-zero integers in Rust, or enums. Right, because my simple enum it doesn't if I have 4 tokens, I'm using 4 integer values in a single byte, which means the 5th value can be the non of an option. This is also true for result. With one asterisk, that the error in the result has to be 0-sized, right? So it has to be either the empty tuple, or it has to be, you can make a custom 0-sized struct with no fields. If you ever wonder what's the point of structs that have no fields, well, here's one use case where I can make a named error. Well, okay, this is invalid token error. Give it no data. I don't need any data. I just need to know, okay, this is an error, whereas the input is just invalid. So as long as the error is 0-sized, basically the result of T and E where error is 0-sized is basically the same as option, right? The same thing where the OK can have some value, but the error is 0-sized, so it doesn't have any values. Therefore, I can sneak the tag for the error into the value space of the T. And the fun thing is you can also nest those, right? So if I have an option of a result of a T, if there is enough value space free in the T, which there's going to be in our token enum, there's then the compiler can figure out, okay, I can use one of the values in the value space for the error and one for the values in the value space for the non and the wrapping option. So we can use this. We can change the way our function works. Can make it a bit nicer to operate on, because if I look at the code here, I only return an option of a token, right? Which means if I'm at the end of the source code, I get a none, which is fine. But if I got an error, I also get a none. And I probably want to differentiate between, okay, I've run into the end of the source code and therefore I get a none, versus I'm somewhere in the middle of the source code and there's an error. There's a sequence of bytes I didn't expect, and that should be an error, right? So there should be 2 different things. So I can abuse this fact that I can nest enums into each other without increasing the stack size, and basically get the error handling at no cost, hopefully. So I'm just going to rebuild my table, but instead of using none, I'm going to use the result where error is empty tuple, because it's ideally it should be like a named struct with some error. But for the purpose of the document, I'm just going to use the empty tuple. I construct it exactly the same way. except instead of sum of token, I use OK of token. And then my method for getting the next token, again, it's roughly the same. The important change here is the signature of the return type of the signature of the method, right? So I'm returning option, so sum of non-values, and the value can be either OK token or it can be an error, right? Beginning is exactly the same, except when I index into the table, I don't use the question mark operator at the end because I want to know, okay, this is an OK token or an error, so invalid token, right? Increment 1, and then again, this is roughly the same. The comparison to like the last token is the token not OK token. This equation, like this stack is also the same because when it compiles like assembly, because OK or token operator is the same, is going to be like in memory, and like the register in the CPU is going to be the same, just 1 byte of the same byte value as the just token operator. Because of the reason we just talked about, right? Everything else is the same, and at the end I just return sum of a token, so it's going to be some OK token or some error something, or or if it has exited at the bytes next from, then it will be null. And again, always benchmark things. So I have my benchmarks, and the getting the lexer with the table of error handling, I have the same performance as before. So I added an extra error handling using the nested enums, and it costs me nothing. Like it's just free. It's a feature that I added, and I have not paid anything for it in performance. Alternatively, instead of doing any of that, you can just use logos, and it's gonna be pretty fast. So summary: embrace UTF-8. Just figure out. I strongly recommend like looking up UTF-8. Is the way it's done is very clever. Also, the way ASCII is designed is also very clever. You can reduce complex match expressions into lookup tables. I would always benchmark things because there are cases where the Rust compiler can actually optimize, and ideally it does want to do that when it can optimize match expressions into lookup tables like itself, like behind the curtain. Most of the times when it doesn't do that is because the match expression is very complex, it has a lot of patterns, and the patterns are just disjoint, or like if you use like the underscore pattern at the end for like anything else, usually that avoids the lookup table then, and like has to introduce branching, and then branching, this performance cost. And you can nest simple enums without slowing things down. Yeah, that's it. Thank you. Any other questions?
Thank you, Maciej. There is time for questions. We have fews. First of all, thank you for the great presentation. And the first question: what is different between tokenizer and lexer? Is there any difference?
No, it's just a different word for the same thing. I think lexer is like the more academic word, because token is like a heavy gravity word, right? It's like in the terms of like, okay, token can mean like almost anything, like lexer is very like specific, and then so you have a tokenizer that splits the source code into tokens, or you have a lexer that splits source code into lexemes. But usually I think the usual convention is we call the lexer a lexer and the token a token. But they are interchangeable. Like if you say tokenizer, everyone knows what you mean, and if you say lexeme, everyone knows what you mean.
Okay, thank you for the answer. If the language expects that word can be both an identifier and a string literal, how should our tokenizer define this word? Or is it better not to do tokenization in such case?
So the second question, you should do tokenization. What you would probably want to do is there might be a different use case for this, but usually you would just define it as a word, and then the important thing about lexer is like lexer is not aware of the context, right? Lexer is just like if I'm reading as a human, if I'm like looking at a page, lexer is that part of your brain that like combines multiple letters to form a word, but it doesn't care about the order of the word in a sentence. It doesn't, it doesn't know anything about the sentence. It's just like, okay, I'm just, what is the bunch of letters? What word is this? Right. So the lexer is not aware of any context. It shouldn't be. That's what the parser is for. And so like actually Rust is a good example of that, right? Rust has cases where some things can be and actually Rust doesn't necessarily have a keyword. If you write if you play at any time with proc macros give you access to a token stream as it comes from the lexer in Rust compiler, and it doesn't have a keyword defined necessarily. Instead of like all the keywords are also just identifiers, and then the parser when you parse Rust source code, you just check, okay, well, I'm expecting a keyword, so I'm just, instead of expecting a keyword, I'm expecting an identifier of a specific string value, like fn for function. And in case of Rust, this is actually useful because we now have like contextual keywords, right? So async it could be used like as an identifier in the past, and now it became a keyword kind of, but it's a keyword only in a specific case, like a specific placement, it can become a keyword. So yeah, if you have like a thing that can be either can be both, it can be contextually a keyword, but it can also be used regularly as identifier, and you just make it an identifier, and then your parser will have to like, because the parser is aware of the context of what it is actually parsing. I'm like in the middle of parsing a function, and therefore like I can expect that there can be if the next identifier is async, oh, this is not a name of the function, it's actually the async keyword, and then I expect another identifier to be the name of the function, right?
Right. Thank you, Maciej. If you are not satisfied with the answer, you can ask other questions or clarify your questions. And the next question, is lexing a context-free operation? Is it parser's responsibility to try to understand what the input about, like function signature or variable declaration?
That's correct. This is actually kind of a common problem I have when people like open an issue on Logos and it's like, hey, how do you do this thing? And it's like, you shouldn't. Like this is like people like find Logos and they try to make it a parser, and in some cases you can, but like if you find yourself like where you in a situation where like you need context, then yeah, you need to build a lexer. You need to build a parser on top of the lexer. Lexer by default should not be aware of any context. It should just it is like a very simple operation of like, okay, I'm just gonna transform this stream of bytes into stream of tokens. I don't care about how those tokens look placed. That's a future job. It's like you want to divide your logic into those steps, because putting lexing in some like extra step makes the parsing much simpler. But like if you start putting context into lexer, you're now complicating the lexer, and like, you're adding the very complexity you wanted to avoid by having lexer in the first place.
I see. As I understand, you heavily use macros. Other question, do macros have impact on compile time and readability?
Yeah. Yes and yes.
And if so, why do you prefer to use them?
Well, it kind of depends on the project. So on compile time, they do that compile time because all they do is generate code. So it is a compile time step that you're adding. So they naturally have to add compile time. I think a lot of people are kind of averse from writing macros. In the Rust ecosystem specifically, you can, there's like two ways to approach the problem. You can just like make a proc macro that uses the token stream manually, or you can use something like syn and proc macro 2 and all that, like nice traits we have. That makes the process of writing a proc macro much easier. But because those dependencies are very large, because like syn in particular has like include the entire syntax of Rust. Like, so you have the Rust compiler that has the entire syntax of Rust, and then you're adding a third-party crate that again has the entire syntax of Rust, and so you have like a double parsing to two different separate ASTs, but one as a part of the compiler, one as a part of the proc macro. I'm trying usually to avoid that. I'm trying to, most of my proc macros I try to just use the token stream manually, and I find that that's way faster, just because I don't have dependencies. Although the cost here is that then the macros can become much harder to read. This also depends, like if you like writing macros that specifically deal with Rust code, right? So are you transforming Rust code into Rust code, or are you transforming something else? Like maybe you're writing your own like domain specific language in Rust. Then you almost definitely don't need syn, because you're just you just want to take the tokens and do something else with them. Like my Cobalt is my crate where I'm using proc macros to make like HTML representation that constructs virtual DOM, kind of. It's not exactly the virtual DOM, but it's like JSX in Rust. So you kind of need proc macro for that, and then it's very useful. And I don't need syn, because syn doesn't actually help me, because my macro doesn't include Rust syntax. It includes like this HTML like syntax, right?
I see. And one question, maybe somewhat outside.
Before one thing I would like to add to that. There's also there's alternative way to proc macros, which we don't necessarily have, and I think it's a bit of a shame. But there's been some work on it. There's some history that involves some drama, which I don't want to talk about necessarily in the Rust project itself. But there's another way to do it. Like a lot of the things we use proc macros for could have been done with like type reflection. And in fact, if you look at Zig, the language, like Zig has like very nice comp times features, and has like reflection. So like stuff we use proc macros for, like serializing to JSON, you could do in Rust the same way it's done in Zig, which is just like you don't write separate code. You just write in Zig, you just write regular Zigs at compile, and use type reflection to serialize to figure out what the types are, and it kind of behaves at the end. It behaves the same way. You have like this compile time code generation that produces like parsing to specific structs. But in Zig, it's actually faster to compile because it doesn't involve proc macros. And I think proc macros is kind of like double-edged sword in Rust ecosystem specifically, because it's one tool that is very powerful and very useful that we use all the time, but it also kind of hides the problems that we have in the language, where there are, if we could do things with, like we could have other features in the language that are hopefully coming in the future that will make some of the proc macros obsolete, and that will actually also improve performance time, compile times and stuff like that, because proc macros, like it's a powerful tool, but it's also like very, like it's a blunt instrument, and it's very heavy to use. So, it's like it's like shooting the fly with a can kind of situation in many cases.
Are you saying that Zig language has some function of proc macro and reflection built inside compiler?
Well, not inside the language, kind of. Like the main advantage, like the main good thing about Zig is like it's like the whole comp time feature, where it doesn't have generics and doesn't have proc macros, but it has this comp time feature that kind of functions as both. Or like it actually doesn't need generics and doesn't need proc macros. There's things you cannot do in Zig that you can do in Rust. So like again, like my Cobalt, like you would not be able to like write like completely custom like domain specific language that uses like non-Zig syntax in Zig, but you can do it in Rust, because proc macros are way more powerful than the comp time powerful in terms of like what you can do with it. But yeah, if you want to like parse JSON or parse JSON string to abstract, then the way, like if you look at the JSON parsing in Zig and then look at Serdi is way more code, and it's way more complex and much harder to understand. It's awesome. Like Serdi is like just perfection when it comes like Rust engineering, but yeah, we could have had a simpler way if only like the language had some extra features.
Correct me if I'm wrong. We can write any domain-specific language in Rust while the language can be handled by lexer. By Rust lexer.
As long as the Rust lexer accepts your input as tokens, then yes. There's even like it's not really used anymore, but there's what's called it's not JS. There was there was a different crate for it was popular for like embedding Rust into WASM, and that had like a JS macro where you could just write a JS exclamation mark, and then you'd write JavaScript code inside Rust code, but not a string, just like a regular JavaScript code, and would like transform that into JavaScript string and like put the variables in, and then make all the bindings for you, and it was kind of magical. I mean, it's still there, it still exists, and it's still like workable. But I think most people now moved to like wasn't binding in that ecosystem. But yeah, you can put like any other language inside the Rust, almost anyway. Like this small asterisk, because the tokens need to be valid Rust tokens.
I see. And a few more questions. One which might be somewhat beyond this out the scope, but I will ask anyway. Any alternatives to proc macros to avoid compile time increase, like code generation? Are you aware of some of such kind of techniques?
Yes. Well, two things. One is declarative macros, obviously, so the macro rules macro.
Yeah.
So if you can make a macro work with just declarative macros, they're almost always faster. And code generation, Logos actually has code generation that was made by me, was made by someone else who like made the contribution. But because Logos is so heavy on code generation, you can basically just take, okay, if you just define your token in a separate file, the same source code, the same code that handles the proc macros, you can just use, okay, I'm just gonna take this Rust file that has the token definition and put it in a CLI like code generator that will generate all the code that macro normally does, and then just like, okay, here's this Rust file, and then just compile with that, and then you don't have to run the proc macro on the compile time. You can just put it in a CLI. And if you do something like okay, I'm doing like a very heavy proc macro thing, but then like again, lexer is actually a very good example of that. Like my lexer probably doesn't change that much, so I can, instead of using proc macros, I could just use like a CLI tool where only if the lexer changes, I have to like rerun the CLI tool and then generate a new file for that. So yeah, that is an alternative. Absolutely.
So is a decrease of time of compilation only benefit of using code generation, or there is some other benefits?
I mean, there is no better for performance gain than doing less work, right? So if you put work that you would do at compile time and just move it somewhere else, like the CLI, and then every time you then compile from that point on, you just compile with already compiled or code generated from the macros already generated. And then yeah, you always win performance because you remove the entire step from compile pipeline, right? So it's always a win.
I see. It looks like one more layer of I don't know, abstraction is not the correct word. We use proc macros.
Pipeline, I guess.
Sorry?
Like build pipeline or something. I don't know.
Yeah, pipeline. We use macros to make some work during compilation and not to do it during runtime, to make runtime faster. And we use code generation to make compile time faster.
Yeah. I'm actually aware of Servo, the like the browser engine. Like again, this is circa like 2016, 2017. I had like a brief look at it, and it was like I don't know how it looks like now, but back in the day, proc macros weren't even a thing yet. And so Servo was using a lot of like Python code to just glue together a bunch of Rust code and then compile that. So yeah, people have been doing that for as long as Rust has been a thing. I'm aware like people have been like using code generation as an extra step to like do things.
Yeah. Few more questions. How does Logos compare with other lexing crates and approaches? Why would you recommend Logos every time, or it depends on, would you recommend Logos every time, or it depends on the use case?
It depends. So I'm not super aware of like how to think. So I know there's like I'm bad with names, so you have to excuse me. Well, there's definitely like nom, which is more of a parser generator. There's another thing where you, I will not remember name. I'm sorry to the author. But there's another crate where you define your like syntax of your language in a separate file that has its own syntax. So it's basically like its own custom DSL for defining the syntax. It's kind of the same way you would normally like if you look at like not academically, but like a white paper kind of definition of a language, then they usually like write like if you I don't know like if you it's like if you look at like WebAssembly specification, like the official one, then there's like a very specific syntax people use to like define, okay, this is how definition of a token, and this is like if you combine these couple of things that are already defined before, then this is the definition of this. So there's a crate that does that where you write in a separate file kind of definitions of your tokens and then definition of a function and so on, and then it writes like an entire parser for you as well. I'm blanking on the name. I'm sorry. But yeah, like I would recommend Logos if you want to write the parser yourself, because I think most of the other crates typically like aim at writing a parser altogether. If you want to just manually write the parser for whatever reason, because you want more control over it, and you just want the lexer, then Logos is the tool, I think. And also because like it's on the interface of what it does, like Logos is very like it just annotation on your variants. Like there's Logos adds very little like code to your that you have to write to use it, right? You could easily like in the future rip Logos out and write your own lexer, and everything else would stay the same, right? It's not very invasive.
From the same author, did you mean like Yak and GRM tools? It is an example of crates. Yak has implementation in Rust, and GRM tools has crate named lrlex. Maybe you are aware about it, no?
I might be aware, but I'm thinking of something else. I'm still blanking on it, but I don't think it's those two. I think there's something else I'm thinking about. I don't know if it's still maintained, so this also might be a factor. I just know I just remember it had like a really cool logo.
Okay, moving to the next question. Can you please elaborate on some common pitfalls or challenges developer might face when writing a lexer and how to overcome them? Basically, your presentation about that, but maybe you can add something.
Sure. Common pitfalls. Well, stuff like parsing like string literals can be surprisingly tricky. Or so string literals, okay, start with double quote and then you parse until the end of another double quote, but then okay, you can have escaped characters in the middle, right? So you need to find out like okay, if there's a quote, double quote with an escape backslash whatever in front of it, then that's not the end of the string, and so that can be tricky. And then like if you do something like Python strings that can have like the triple quote, or like Rust where you can have like raw strings with like R and then multiple hash characters, and then at the end there's a double quote with the same number of multiple hash characters. That can be tricky. Comments can be tricky, surprisingly, both like block comments and like the line comments. Line comments I think are a bit simpler, but like block comments specifically can be quite tricky when you have like much things inside of it. Yeah, I think that's mostly it. I don't know. Even like something simple like numbers can be sometimes surprisingly tricky. Because like the way I actually did in presentation, now I did number, I did like, okay, it's and I did it 0 to 9 repeated. But out of the time, if a number begins in programming language all the time, like if a number begins with 0, it expects to be just be 0. Like you wouldn't write 10 as 0, 1, 0, right? You would just write 1, 0. And depending on the language, you might allow or not allow the syntax. So there's some trickiness there. As it comes to pitfalls, I don't know. I think that's mostly it. I think parsers are way more tricky, especially like based on language you're trying to parse. Like oh god, like arrow functions in JavaScript are hell. Like because up until you get to the fat arrow, like the list of arguments can be just like a sequence in parentheses, like a sequence of variables in parentheses, which for some reason is valid JavaScript. So like JavaScript has like this like syntax ambiguity until like you meet a certain token, which is also like interestingly, if you ever wonder why Rust is using like the pipe character for closures, it's because there is no operation where the pipe operand is the first token in an expression other than the closure. So the Rust is using the pipe because it's the unambiguous token. So it never has to. There's never an ambiguity. There never has to like backtrack the token stream to figure out what's going on. If the first token in an expression is a pipe, it's always a closure. That's why it's pipe, and body.
I see. Thank you for the answer. And a few more, and we are ending. Is it possible to do the same JS code embedding as we do often in Rust in Zig programming language? If you can answer the question.
I don't think it is.
Okay.
That's the answer. I don't think it is.
Okay.
Especially since in Rust you can do a lot of it. Like even if you don't use the token string directly, you could make a program code that takes the JavaScript even as a string, and then you can in the program macros you can take that value of that string, and then you can start parsing that manually by like you could make a proc macros that takes the value of a string of a JavaScript and then use logos inside the proc macros. So now your proc macros have proc macros, and then you can parse the JavaScript there, and then do something with it. So yeah, like again, like proc macros are way more powerful than like the complaint in Zig, but Zig is like somehow nicer, even though it's like more limited, but it's nicer and generally compiles faster.
Okay, and the last question: what is your favorite tabletop game?
Oh god, I don't have a good. I actually have designed my own that I've probably by now played the most. It's not public yet though, but it's like a 5 versus 5 skirmish war game. I really like just from design standpoint, I really like Frostgrave. Just because again it's like very simple streamlined mechanics. I quite like that. I played by a bunch of Warcry. Yeah, I don't know. I also like play like role playing games, so D&D and adjacent stuff. But yeah, like typical war games like Warhammer, like the big Warhammers. So that's too much, too many models to paint, too much to manage. So like it's mostly like the skirmish games and like role playing games for me.
I see. Maciej, very thank you for the participation. We are very glad to see you here and for sharing your experience.